Okay, so we just summarize for you all that we have learned. Your magnetic flux, flux linkage, Faraday's law, this is Faraday's law, and then there's your Lenz's law. Right? Oppose, remember oppose. That's why we have a negative sign there. Okay, let's go to worksheet 23, page 268. Anyone like to try that? Magnetic flux? Yep. Review, come on. Memory work. Anyone?
Product of magnetic flux density and area of the field passing through.
Okay, but you must have the area normal to the flux, line of the flux, or magnetic field strength. Okay, product of magnetic flux density and the area normal to the flux, line of the flux. Define magnetic flux density. Yeah.
Per unit current per unit length.
It's just a magnetic field strength or magnetic flux density is defined as the force per unit length per unit current on current carrying conductor placed at right angle to the field lines. Right? And then flux linkage for n turns is just times n. Total flux. Okay with that? All this you must know. All these are what I call points that you can gain. This for 1 turn. This for n turns of the coil. So it's the total flux passing through n turns. Okay, copy already. Just refer back to your note lah. Easier rather than copy. Right? So BAN. Sin theta if you want. State Faraday's law. Anyone? Yep. Anyone want to try? Just force it into your head. Anyone?
Induced current or induced EMF is established in the direction as such it produces effect
No.
that oppose the
No. That's Lenz's law. That one is Lenz's law.
Oh,
David, don't get confused.
Induced EMF equals to negative change in magnetic flux.
Rate of change in flux linkage. Right? Induced EMF is proportional to the rate of change of flux linkage. What you see is just Lenz's law. Okay. It's a conservation of energy because when you push a magnet into a coil, you have an induced current flow to produce an opposing field to the magnet. So in this case, your mechanical energy transforms into electrical energy. Okay, got what you want? Okay, I'll change to the next slide. Okay, calculate. Let you calculate first before I go over the answer. Look at Barry, is these days very early. What happened to call? Still not here. Right? Identify, there's your N. That's your area. Remember to change it to meter square. That's your initial, BI. That's your final, 0. That's your time, 5 seconds. And just use your Faraday's law. Right. Replace your flux linkage with N times 5. and then becomes your BAN. Okay, so what is changing? Take the constant out. A can take out and take it down. What is changing is B. Right? Change of B with change in time. Right? N and A are constant. B is the one changing, final minus initial. So N is 1000. Right? B changing to meter. Initial, final one is 0. Right? Final one is 0. Initial 0.75. Time is 5 seconds. And calculate out. I said don't bother about negative sign. 0.53 volt. Okay, let's look at how the flux change and how the EMF induced is also changed as the rectangular coil move into the region of magnetic field at constant speed. Right? This is your region of magnetic field. Go inside. Right? This is the area that's inside the coil. That's the speed. That's the rectangular coil. So area is just this area inside the coil is just your L times your W, or W times L, and your flux linkage. If it's 1 turn, it's just B times your A. If it's perpendicular, then replace your A with this one, WL. And then since speed determines the length, we can replace this length with the speed and the time. Distance is your speed times your time. Place it inside there. Then we can see, readjust. B is constant. Inside the region is constant. W is constant. L is the one that is changing. Right? We replace with V and T. T is the one changing now. So BWV is constant. So that's the equation of a straight line. Okay. That's how the graph will look like. When the coil is completely inside, there's no induced EMF because the area is constant. Right? Inside there, area is constant, not changing. Only this part, as it move in, area start to increase. So that's why it start to increase. When it's completely inside, right? Flux is constant, doesn't change. Okay, how does the EMF look like? Anyone? Come, talk to me. The one need to give you the answer. You tell me the answer. Yep.
Increase then constant.
Then
decrease.
Inside the field, when the coil is completely inside the field, what happened?
Constant.
EMF. Remember, you are using gradient. Gradient is the rate of change of this one. You're using gradient of this one. Gradient of this one. Gradient of this one. What should it be? So this part should be constant. This part. When the coil is completely inside, what happened?
0.
0. Then this one.
Deceleration. Negative. Constant.
Important. You cannot show positive. Must show negative. Right? Don't bother about the negative sign. This one tell you we use a gradient. Right? So that one is you can put negative if you want to. Then 0. Then after that is negative. Okay. Same slope. Same height. That's important. They're looking for same slope, same height. And these two are in different direction. One positive, one negative. Okay.
Sir, I need to leave early.
Okay.
Sorry, sir. Got something to do. Thank you, sir.
Okay, let's look at this one. Two similar coil A and B of insulated wire, one on a soft, right? This is a soft iron core. Right? That's our next topic that we'll go into. When the current in the coil A is switched on and then off. Okay, That's what graph we see. Anyone can explain to me why you see this one? Huh? This is what we have studied. When you turn on the switch, why the current doesn't go on straight away to constant value? Anyone? Yep. You don't need to know. This is called self-induction, but you can explain to me. Anyone?
Because you induce another current.
Okay.
Oppose the magnetic field.
First, the current is going to start to increase very fast to the maximum value. So when current increases, the magnetic field starts to change. So the flux will cut the wire itself. So there will be induced EMF to oppose the induced current or induced EMF oppose the direct current.
Oh.
Yeah, not overcome the resistance. Right? Because the current is going to go to increase very fast to the maximum value.
So there's a change in
Right? That maximum value. So it's going to change very fast. So the flux change very fast. So the current opposing it, the induced current opposing it will be very large also. Right? Then when it slow down, then it start to increase. Oh. That's why you got this part there. Then after that, the current reach constant. Then when you turn off, by right it should decay lah. But this one it just give you a straight line. It just want to see whether you know how to draw. So how should the EMF look like? Anyone? No, resistance doesn't come in. Resistance do affect the curve slightly, how fast it will go up, that's all. Then the current increase very fast, so the flux is changing very fast. So that is the one that produces the induced EMF.
So greatest up.
So we call that self-induction, no? Because it induced in the conductor itself, in the primary itself. Okay or not? You don't need to know that far anyway. This is just a side issue to try to explain to you why it go the shape this way when you turn on the current. Right? That's a side issue. You want to learn, want to read that, it's called self-induction. Right? It's an exponential rise. Okay? Your job is to know how to draw the induced EMF. How does the induced EMF look like? Anyone? Yep. Anyone?
Decreases with it.
You mean it go like that? Is it?
No, straight line.
Straight line like that?
Straight line decreases. I think so. I don't know lah.
I will shoot you all. Don't know. This one you want to find the gradient. This one is like vertical, very large. After that, the gradient start to decrease until you get to 0. Okay?
Justice for Josh.
Yeah? B is proportional to I. Yeah? The current changing. The current is the one that produces a magnetic field. Then we go to EMF. EMF is just the rate of change of magnetic flux linkage. And magnetic flux linkage BAN. Right? So ultimately, E is proportional to the gradient of the tangent to the curve. So this part is like maximum. Then it starts to decrease to 0. Okay, like that. Then this part is 0. Right? Gradient is 0. If this part is positive, then this part must be go negative. That way. Yep, can. Okay or not?
So
Yep.
The B is proportional to I.
Yep. Remember, we are looking at here. We are looking at here. We're looking at here. You turn on the put on the switch. The current is increasing here. So the field is going over here. Also start to increase. So the changing current, changing magnetic field, and then changing flux linkage across here. EMF is induced across here. Keep that in mind. Right? Get the perspective right. What is happening? Okay. Okay, let's go to the next one. If you're happy with that. Right? As I say, this is self-induction. A slight extra knowledge you want to learn. Right? Not in your syllabus. Okay, let's look at this one. Elliptical spring, just a spring lah. Don't bother about the elliptical. It's clamped. This is part is clamped there. Free end of the spring is attached to a sheet aluminum and a mesh. Okay, there's your electromagnet. There's a DC supply. There's a switch there. Right? So remember, electromagnet is your source of magnetic field. That's how your magnetic. Right? Just know what is happening. This is your flux. There's your magnetic field. The lines there. And if the aluminum sheet is moving, it's going to cut this magnetic field. Okay, so got your rough idea. Changing flux across the aluminum causes induced current to flow in the aluminum sheet there. Okay, electromagnet is placed near to the center of the aluminum sheet. The mass is displaced vertically, and with the electromagnet switch off, the mass is released. That's how your spring, right? Magnet, remember the electromagnet is off. That's how the displacement time graph is simple harmonic motion. Okay, go back to the previous slide. Right? As soon as you see this picture, you should start analyzing in your mind what is happening here. This is testing you electromagnetic induction. It's also testing you simple harmonic motion. So that's why I say it's a popular question, electromagnetic induction, because it can test you magnetic field, can test you electromagnetic induction, and tell you simple harmonic motion. So every three topic is counting inside one question. That's why very popular. And it's poor. The examiner comment that is poorly done by the student. Okay, got what you want?
So what is happening?
What is happening? They will take you through. First, electromagnet is switched off, and then you displace this mesh, pull it down, and that's what the graph you get. That's the graph you get. How the displacement change with time. Right? Now you're supposed to apply. The electromagnet is switched on, and the experiment is repeated with the same initial displacement. They told you already, damp oscillation is observed. They are very kind to you. So you should know how to draw the graph already. Lightly damp. Right? So that's your exponential. And draw. That's all. Right? Lightly damp. Lightly damp oscillation under simple harmonic motion. Go and review. Okay. So this one is exponential. These two dotted line. Exponential decay. And if you draw, take this maximum point there, you draw is like exponential lah. Right? Lightly damp. Like that. That's how it should be drawn. Have to care for internet. Okay with that? Lightly damp. Okay, right? This part is exponential. This curve there is exponential. Then this part is lightly damp. Okay, anyone like to state Faraday's law? Right? They take it through step by step. Then after that, they want you to use Faraday's law. Yep. Anyone? Oh, very quiet. No one want to try. Anyone? State Faraday's law.
Induced EMF is proportional to rate of magnetic flux linkage, rate of change of magnetic.
Okay. EMF induced is proportional to rate of change of magnetic flux linkage across the circuit. Right? Usually we won't worry, as I say, we won't worry about the negative sign. Right? Because negative sign tell Lenz's law. Okay? So EMF induced is proportional to the rate of change of magnetic flux linkage across the circuit. Explain why the oscillation of the mass are them. Anyone? Yep.
Loss of energy is it?
Say again.
The energy is lost to electrical energy.
Step by step lah. Don't jump lah. It's so many marks there. You just get only 1 point.
Oh, I thought one line only.
No lah. Cannot say one line only like that. This one must go step by step explanation. You explain the middle there. How to have everyone can understand what you are doing.
I also don't know what is the concept. So you explain.
Explanation is correct, except that you jump to the middle there rather than start from beginning.
Oh, so what happens at the beginning?
Okay, the moving aluminum sheet, what happened? It cut the magnetic flux.
Okay.
Right? Magnetic flux. Producing an induced current in the sheet there. It's moving across the magnetic field. They cut the magnetic field, so you have the changing magnetic flux. So they produce the induced current or EMF in the sheet. So where the induced current flow, it will produce a force opposing the motion. So in this case, the mechanical energy of oscillation is converted into electrical energy. So it means the mechanical energy becomes smaller. That's why it's damped. Right? Amplitude becomes smaller and smaller. Okay with that? Usually this one is 2 to 3 marks, I think. So explain step by step.
Okay.
Sorry, it should be magnetic field. It got the magnetic field causing a change in magnetic flux. Okay, it got the magnetic field of the electromagnet producing a changing magnetic flux across the aluminum sheet. Then you produce your induced EMF. Look. Okay, got what you want? Suggest how critical damping could be demonstrated using the apparatus. How? Anyone?
Increasing the current.
Then 1 mark only. Usually this will be 2 marks. How do you know it's critical damping? Keep on increasing the until what?
Oscillations.
What about the oscillation?
Oscillation, less oscillation per unit time.
Less oscillation means that is your light damping. But you want critical damping.
Oh, I forgot.
So critical damping must means that when you displace it, come back to the rest position, no oscillation. Right? Important. Right? So you increase your magnetic field strength, correct? You get your first mark. by increasing the DC supply until the sheet when displaced return to its rest position without oscillation. Okay, that's the second mark. Okay or not? Not what you want? Okay, looks like I think we have to stop already. But if those who want to stay back and ask questions can stay back. I think you got next class at 10 o'clock. So that you all get ready for your next class. We'll see you for the test on Wednesday, and then we'll carry on to AC. Try all the example there. Right? Try all the example there. We will go over the question, then go to give you the test first, and go to finish the worksheet, and then we go to alternating current. Okay, thank you. You can go. If you want to stay back and ask questions, you can stay back. We still got 10 minutes.
Bye. Thank you, sir.
Oh, normal idea.
Thank you, sir.
Okay, bye-bye.
See you soon.
Bye, 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 bye. Bye-bye, Barry. Bye-bye, Jiro. Anything you want to ask? Okay, I'm ending it now.